Okay, here we have a problem where we're going to actually be using those formulas. This one says the number N of bacteria present in a culture at time t in hours obeys the law of uninhibited growth. According to this formula, N of t equals 1000 e to the 0.01 t power. Now, if you'll remember back at what we looked at earlier, we had a formula that said, oops, that's in yellow, sorry about that, that we had N of t equals N naught e to the kt. And we said this N naught here in this position is or 8 could be A naught and A, doesn't matter, that this is always our initial amount or our starting value. The K is our proportionality constant, and the T is our time. The N of T, or it could be A of T, is our amount after time, our number after time. Okay, so that's just kind of to refresh your memory about where this formula is actually coming from. Okay, part A here says determine the number of bacteria at T equals 0 hours. Well, part of this, once you understand the way the formulas are set up, you could read that off immediately. But, before that, or, at any time, you can always plug it in. If t is 0, then that means we are evaluating this function for a t value of 0, which means we'll have 1000 e to the 0.01 times 0 power. Well, anytime you multiply 0 times something, that's automatically 0. And e to the 0 power, well, anything to the 0 power is really a 1, isn't it? And 1000 times 1 is 1000. So at time 0, our number of bacteria present is 1000. Well, if you think about it, that makes sense also, because at time 0, that's when you're starting. That's your initial time, your initial amount. And look what's in that initial amount spot in our formula, the 1000. So that's exactly what it should be. Now part B says, what is the growth rate of the bacteria? The growth rate is just another way of saying the proportionality constant. It's what keeps that happening at the same rate each time. If the k happens to be positive, that means it's a growth function. And we talk about k as being the growth rate. It's not just the proportionality constant, it's actually the growth rate. If k happens to be negative, then this thing is going down or decaying, decreasing, and then we would call it the decay rate. So in this case, our growth rate comes directly from that k value. Well, our k value was 0.01. The only thing when we talk about growth rates and decay rates is generally they're in percentage form. So if I were to change this over to a percent, I would have to multiply by 100 or move the decimal over 2 places, which would make that a 1% growth rate. Now for part C, we're going to be graphing this thing using a graphing utility, but I think I'm going to wait for that for just a minute. Part D says, what will the population be after 4 hours? Well, again, here we are given a time of 4, so that is just an evaluation. We're figuring out how many bacteria there are after 4 hours. When we start with 1000, we have a 0.01 growth rate. So now we want to make sure, and we want to do you could do this all on your calculator in one fell swoop if you wanted to. You just have to make very sure that you put the entire exponent in parentheses. So 1000 e raised to the 0.01 times 4 power, close, close, we should get 1040.8 bacteria after 4 hours.